So how about big omega notation? So we're looking for the best case scenario. So we're looking for the least, okay? The least value, least time to process our data, our, our algorithm to give us an output, okay? So this is the formal definition for big omega notation. Function at n is said to be big omega g at n. If there is a constant c greater than 0, so we multiply a certain value to g at n, and it will be smaller with the function at n. Okay, even we multiply value to g at n, still it is smaller or equal to the function at n, wherein n is greater than or equal to n0. Again, n0 is the start value wherein the cg at n will become smaller than the function. Okay, so as you can see on this graph, so this is the function at n, and then on a certain value, okay, which we call it n0, cg at n will become smaller. Okay, so so it will be constant smaller compared with function at n on a certain value. So this is the equation that we're going to determine for the big omega. So we look for smaller than the function at n. So that's the thinking. Okay, so let's have this example. 2n squared plus 3n plus 5 and the g at n squared. So we're going to check if n squared could be considered as big omega notation of this function at n. And don't forget, c times g at n should be less than or equal to function at n. And what is g at n? N squared. So c times n squared should be less than 2n squared plus 3n plus 5. Then, to solve for c, we just divide the right side by n squared. So the result will be 2 plus 3 divided by n plus 5 divided by n squared. And we all know that when n reach to infinity steps, what is the effect in 3 divided by n 5n squared? It will be negligible kasi it will be too small. So the only factor when n near to infinity or infinity, the only value that affect RC is just 2. So therefore, RC is equal to 2 multiplier to g at n. Okay, so let's substitute here. 2n squared less than or equal to 2n squared plus 3n plus 5. So let n is equal to 1. So 2, we solve for 2n squared. And for the right side, it will be 2 plus 3 plus 5, which is 10. So this is correct. And when we increase the n, still 2n squared is smaller compared with 2n squared plus 3n plus 5. Therefore, the n squared is big O notation of 2n squared plus 3n plus 5, wherein c is equal to 2 and greater equal to n0 is equal to 1. Okay, so the first value is 1. Don't forget, c should be n should be greater or equal to 1. So beyond 1, still the equation is still smaller compared with the function at n. Okay, how about this example 2? So same, 2n plus 3 g at n is equal to n. So again, the function should be bigger compared with the c g at n or cn. Okay, so when we solve for c, so the result could be either 1 or 3. It depends on you. Okay, since we're going to divide, since we only care that c or g at n should be less than. Okay, so when we divide both sides, c, and when we substitute 1 rather to c, 1n is less than 2n plus 3. If it's 2, still this will be small Okay, but if it's 3, there is a possibility 2n plus 3 will be smaller compared with 3. So we need to look for the value of n wherein will it be false. Okay, so basically C and the value of n should what do you call this, should conform with the CG at n less than the function. So when you increase the C, check the value of n, will it be still true to a certain value? Okay. How about if g at n is equal to log n? Definitely log n is smaller than n. So definitely it will be big omega log n for a function at n. For n squared, definitely based on our previous discussion, n squared is bigger than n. So no need for solution. So it's not big omega. Okay. So again, note C times g at n should be less than or equal to the function n at n wherein n greater than or equal to n0 and c is greater than 1. Okay, so you could do the mathematical operation. Okay, well, that same as what we have did on the previous slide. Okay, now let's discuss theta notation or theta notation rather. Okay, so function at n is said to be theta notation g at n, big theta g at n, if there are constants c1, okay, and c2 greater than or equal to 0, and a natural number n0 such that c1 times g at n less than or equal to function at n less than or equal to c2 at g at n for all n greater than or equal to n0. So as you can see here, we have g at n on both sides. The only difference is c1. So when you multiply c to your g at n, c1 g at n should be smaller than the function at n. While when you multiply it by c2, it will be bigger than the f at n. Okay, so you need to be consistent with the g at n. It should not be different. We all know that in big omega, so it could be different notation as long as it should be smaller than the original function. Well, same as with the big O, you could have different notation as long as the notation is bigger. But for the theta, the g at n on both sides should be the same. If this is log n, this should be log n. If this is n, this should be n. Okay? That is our rule for theta notation. Okay, so for example, so again, 3n plus 2, g at n is equal to n. So we already discussed the c1gn, and the previous slide should be less than or equal to function at n, and it should be less than or equal to c2g at n. From previous example, we all know that this is big omega n, wherein c is equal to 1, and greater or equal to n is equal to 1. While for the C2 big O notation, we already solved this on the previous example. So again, 3n plus 2, 3n plus 2, and 5n, wherein 5 is C1, and n greater or equal to n01 is equal to 1. Okay? So when we evaluate this, n will always be smaller than this function, and 5n will always be bigger than this. So the theta notation is this range. Okay, same function but different multiplier. So that's theta notation. Okay, so that's it for this video lecture. So see you on the next. Thank you for listening.